Afternoon, everybody. I am Luke Borcjes. I'm doing my master's at the University of the Western Cape. My research is on model-free deep reinforcement learning for cybersecurity in software-defined networks. And on this presentation, I am exploring the impact of adversarial learning in that area. So onto the presentation outline. And some interpretation outline. Initially, I will just go deep dive into the causative attack, the adversarial machine learning that was used. And then we can look at the results and we can go into the conclusions. So about the work. So first of all, this work is a continuation of previous work, which is model-free deep reinforcement learning in software-defined networking, applied in the scope of cybersecurity. Now, what that work did was it compared two algorithms on their viability, the first being double deep Q networks, which we'll look at, and then the second being neural episodic control to deep QN, which is a more recent algorithm. And in this presentation and in this work, we explore the impact of adversarial learning on the two deep reinforcement learning algorithms used in the scope. And the objectives is to determine whether the implementation of the adversarial machine learning would create a more robust defending agent, and then to explore the impact on the overall system, and then to try and get a better overall engagement from the defending and the attacking agents. So the motivation is to leverage adversarial machine learning during training as a means of training more robust agents, and to explore this means of getting more engagement from the attacking agent in the network as well, because previously when doing comparisons, the attacking agent was entirely dominated by the defender. And so when doing this work, many challenges were faced because it is extremely complex to implement and to build, because a capture the flag system had to be implemented into an emulated network, which is run with a zero-sum game format, and then we had to set up some form of server-client communication, so network can flow and there can be some type of communication, and then now there's implementation of the adversarial machine learning. So what is software-defined networks? So software-defined networks is an architecture that allows networks to be efficiently programmed, monitored, controlled, and optimized accordingly. It comes in three layers. We have the application layer, we have the control layer, and then we have the infrastructure layer. Now, the advantages to this is that the software-defined networks runs on a software level. This makes it easily accessible via virtualization. It means you can easily prototype and on top of that, it is overall cost effective. And as well as that, it separates network control and forwarding functions. And the network resources can be conveniently managed. And the architecture allows for open source controller platform. And Ryu is a component-based software-defined networking framework, providing APIs to create, manage, and control the network. And this is just a high-level overview of what the agent will see, and also in a way that we can interpret what is going on in the capture the flag system. All nodes which are initially compromised as the starting points are marked in red. All nodes which are your normal hosts, your normal systems, are marked in green. And your target host, which have all nodes which are initially compromised as the starting points are marked in red. All nodes which are your normal hosts, your normal systems, are marked in green. And your target host, which has the server flag which has to be captured by the attacker, is marked in blue. And your ones which are marked in yellow or orange are the server migration candidates, which will be used to be able to migrate and move the server in case it felt it was under attack. And so for our first algorithm, we use the double deep Q networks algorithm, which is a well-known algorithm in the field of deep reinforcement learning. And for the second one, we use neural episodic control, which is a much more newer algorithm that was explored in 2018. when looking at the agents, in order to represent the state of the networks, we used a binary NumPy array of length 80, where we have a total of 32 hosts and 48 links. If a host is compromised, is marked with 1. If a host is not compromised, is marked with 1. If compromised, 0. If a link is active, it's 1. If inactive, it's 0. And because we have attacker and a defender, we need a way to classify them and to separate them. We have red, which represents the attacker, and blue, which represents the defender based on their roles. And for the action space, which is a discrete action space, we have 32 actions for the attacker and 64 for the defender. And for the single action rewards set for the attacker, we have -1 and 1. For the defender, we have -1, 0, and 1. So onto adversarial machine learning. Now the adversarial machine learning is the study of attacks done on machine learning algorithms, and is used in machine learning to misguide a model using malicious input. And maliciously altering the input for deep neural networks with adversarial attack can easily fool it into those, because most of the deployed cyber defense systems that are still rule-based actually still use human interactions. And when using human interactions, what it does is it allows the opportunity for a human it allows the opportunity for a false alarm or a false input. And so your defending agent, which running in the background, has to still be able to make an optimal decision with that falsified input. Okay. And so for adversarial machine learning, you can mean different types of attacks. And so for this research, what was chosen was to do a data poisoning attack implemented through state perturbation of the input state of the agents. And since a state at any step t is an input array, as mentioned earlier, what then is done is that in order to implement a false negative or a false positive, all that has to be done is we have to change, or all they have to do is then change a 1 to a 0 or a 0 to a 1. And so let's just take a quick look at the algorithm. And so this is the causative attack algorithm that is used. And so how it works is that what we do is we take the input state from the original experience, and then we iterate through all the nodes, and then we can falsify them, and then we can evaluate what the estimated Q value is. And the estimated Q value, which gives us the best results, is stored. And from those stored ones, it's then implemented and then injected into the original experience, and that gives the altered experience, and then that is used for the training of the agent. So onto the results of the data. And so in order to record results, we ran 2 different games where the roles are swapped. And for the first set of results for each game, we have up 10 game runs with 5,000 turns. For the second set, we have 10 games, 50,000 turns, and for the third set, we have 10. And for the third set of 10 games, we have 500,000 turns. And so what we see, although for sets 2 and 3, it had actually taken much more turns in order to win the actual games, although for these sets, they had managed to win the same amount of games regardlessly. So onto the attacker for the first game, which is double DPN, and it had actually won less games for set 1, which is why we see a lower average. although for set 2 after implementing the attack, it actually had a worse performance against the defender, ironically. Although for set 3 it had improved and it managed to win its games with a much more improved average. And it managed to win its games with a much more improved average. So on to game 2 for the defender using double DPN, and there was no change in win count, even though there was an improvement in the amount of turns taken to isolate the attacker and win the game. However, for sets 2 and 3, it was hit in an extremely negative manner, and it only managed to win one game after being attacked, which actually shows the vulnerability of the algorithm when dealing with falsified inputs. And when looking at the attacker for game 2, which is near epsilon control to DPN, and it had a slight improvement over the defender, and for sets 2 and 3, although we see a greater average in turns taken, we need to realize it played more games and had won more games. So that's also something to take into consideration. And on to the conclusion. So from what we can see from this is that the double deep connected algorithm is much more vulnerable to data poisoning and to falsified inputs, although when compared to your episodic control algorithm. And then we can also see that there was some degree of robustness and improvement in the neuroepisodic control through deep network algorithm, and the engagement level and performance of the attacking agent role was improved, as from previous research it wasn't able to win a single game. So some considerations for the future work is maybe the implementation of randomized starting, the consideration of maybe partial observability of a network. These are my references. Thank you for listening. And here's the appendixes used to where all the other stuff is. Thank you for listening. These are my references. Thank you for listening. And here's the appendixes used to where all the other stuff is. Thank you for listening.
Thank you very much.